I think we can start. Well, good morning, everyone. Good afternoon to the speaker, and welcome to our IPARCOS-seminar. Today, I'm pleased to introduce you Dr. Kohei Inayoshi, a theoretical astrophysicist currently working at the KIAA Institute for Astronomy and Astrophysics in Peking University as a faculty member. Before joining Peking University in 2018 fall, Dr. Inayoshi spent 4 years at Columbia University in the US as a Junior Simons Fellow. He received his PhD in physics from Kyoto University in Japan in 2014. He's interested in a variety of topics on the physics of black holes, including gas accretion physics, formation of supermassive black holes, and multi-frequency gravitational wave astronomy. Dr. Inayoshi was awarded the Young Astronomer Prize in 2021 from the Astronomical Societies of Japan for his research on theoretical studies for the formation and evolution of massive black holes. Today, Dr. Kohei Inayoshi will talk about the age of discovery with JWST, excavating the first massive black holes and protogalaxies. So thank you very much, Kohei. The floor is yours.
Right. Thank you for a nice introduction. So can you see my slide now?
Yes.
Right. Hi. So good morning, everyone, and thank you for waking up and thank you for joining today's seminar. So my name is Kohei Inayoshi. Talking about so today I'm going to share with you some recent aspects about James Webb, also related to the high redshift massive black hole studies. Also, so I show the my collaborators here, but especially I would like to acknowledge 2 students in my group. So today I'm going to show some work, project and the results. So based on their work. So let me start. So this is the outline of my talk. So first I would like to give introduction and overview of the recent observations done by James Webb. And also, I briefly talk about the rapid growth of the seed black holes. And finally, I briefly mention the how to discover first and low mass black hole in a super high redshift. So this is a very general introduction, but let me talk about the the key ingredient in my talk, which is a supermassive black holes. So supermassive black hole with the mass of million to billion solar masses are pretty important and a fundamental component in our galaxy or all the galaxy in the universe. And basically the black holes are located at the center of galaxies and eating gas supplied from the host galaxy environment. So when the black holes are accreting and eating gas, and simultaneously that they in a deep potential well, the accreting matter release huge amount of gravitational energy into radiation outflows. So those so-called feedback process, produce huge amount of energy and momentum into the surrounding environment. So this is quite important to change the evolution of galaxy. So by this process, many people in astronomers believe that. So by this process, both black hole and galaxy, communicate each other. So that's why we're gonna see kind of a tight correlation between black hole mass and the galaxy property as shown in the right-hand side here. So you see in the right-hand side, the x-axis galaxy mass, y-axis the black hole mass. You see very nice tight correlation in mass spanning many order magnitudes. So we believe that, many astronomers believe that those kind of tight correlation can be established by the mutual interaction and the coevolution between 2 components. So based on those observational facts, so we have a bunch of key questions. So I just show the 3 questions, especially I have. So what's the origin of the supermassive black hole? So this is quite important, but we still don't know, we don't understand the origin of those components. And also, as I say, so we don't know, how the 2 important components, both black hole and galaxy, interact over the cosmic time scale. And also, what about the cosmological evolution? And what happens if you go beyond local universe? Okay, so this is a very simple schematic picture showing the history of the universe. So in the left-hand side, Yeah, so left-hand side, so universe started after the Big Bang, and afterwards universe expand, and eventually, now we are living in the right-hand side here. So by the process, we have many theory and observation things, but especially, thanks to the nice establishment and the development of the observation facilities, our observation frontier is getting closer to the early and early universe. And actually our frontier is getting closer to this kind of dark region in this schematic picture. So this region, this epoch is so-called the cosmic dawn or dark ages. So especially after the Big Bang, universe was so hot, all the baryon and gas components so hot cannot collapse. Again, cannot collapse, and then basically no structural formation. But later time, especially the cosmic dawn time, the universe cools down, and the baryon component is accumulated in the dark matter halo potential and start to form structures. So by the time, so theory people believe that something, the first object should form. For example, like first stars, first galaxy, and probably first supermassive black holes. So this is very important time which actually determine the evolution of the universe. For example, the cosmic reionization. And these days, we have we get a very exciting result thanks to the new instrument that this one. So James Webb Space Telescope. So thanks to this very amazing sensitivity of this telescope, so we observe a bunch of high redshift, super distant galaxies, also some AGN components, so which I will basically focus on today's talk. So here I'm gonna show you the, I just try to highlight the overview of the observation of high redshift supermassive black hole population. So here you see the x-axis is redshift and the y-axis is the black hole mass. So here you see the bunch of dots here. That is based on the observations before James Webb. So basically, those data points are obtained by ground-based telescope such as Sloan, SDSS, or Subaru Hyperspring Cam, other bunch of ground-based telescope. And as you can see, based on those observations, the black hole mass is pretty massive, right? So exceeding 10 to the 9 solar masses, and those observations are sensitive to the very bright and the most massive population at the early epoch of the universe. But the situation changed a lot. So the James Webb changed the game, and after James Webb observations, we actually observed many supermassive black holes in such the early epoch of the universe. And around this region, you see more than 10 objects, but now number increases with time. So we have to follow up all the archive papers these days. But anyway, by now, roughly 30 AGN, active galactic nuclei, are observed by James Webb at such early epoch. I just point out somehow famous AGN. So this is a GNZ11. This is the most distant AGN candidate, or maybe spec confirmed, done by Roberto Maiorino. So the redshift is 11, super high redshift. And the second high redshift sources were discovered by Rebecca Larson. So shears 1019. So redshift is 8.7. This is also super high redshift. And also, next slide, I'm gonna show you our discovery. So this is shears 2782 and redshift 5.2. So this was the first discovery of the AGN done by James Webb data. So let me explain this kind of things. Yeah, so after the first data release of the James Webb program, so we dig into the public data and try to find the AGN candidates. So the long story short, but we discover the AGN candidate. Afterwards, in collaboration with the Shears team, which is one of the biggest James Webb group, and in collaboration with them, we try to make follow-up observations and try to identify the broad component of Balmer lines. So here you can see the broad H alpha component right here. Then using the measurement of the line width and luminosity in the AGN component, we try to estimate the black hole mass. So as you can see here on the right-hand side, so this AGN is quite unique. So two reasons. So one is, so this, the ID is a bit changed, but please look at the red star here. So this object is pretty unique because so the luminosity is very faint compared to the previously known AGN component at the same redshift. So this is fainter than them by 2 or 3 decks. So which is quite low luminosity object. Red star here. And also based on the black hole mass measurement, we also found that the mass of this guy is 1 dex low mass. So lighter than other previously known AGN the same redshift. So we actually opened a new parameter space in black hole mass and luminosity plane. And afterwards, I guess so many people get excited and many people try to find the AGN-like object and make sure the presence of AGN in the James Webb data. So here's a highlight. So I cannot show all the James Webb AGN papers, but I just show some example. So right now we spend roughly 1 year after this game started, but we have so far 30 or I don't really know the exact number, about 20 or 30 AGN were confirmed by James Webb observations. And so this is the one example, the spectrum, and also looking at the image here. So we see very, very compact and bright and the kind of red color. So you see the red color images. So based on those information, we try to understand the property of such AGN, especially this particular object are so-called the little red dots. So it looks like red and a very compact morphology. So this is a pretty important phase of AGN. This is like AGN feedback activated, and we might see the transition phase from starburst galaxy to the quasar active phase. But anyway, so thanks to the many observations of the AGN in James Webb dataset, those kind of observations allowed us to put the number density estimation on this plane. In the right-hand side, you see the x-axis is a UV magnitude, the absolute magnitude. So the left is a fainter. If you go to right, it is brighter. And the y-axis is the number density of such object. And before James Webb, we had a nice constraint on this is so-called quasar luminosity function. Okay, so we have a nice constraint of quasar luminosity function based on the ground-based survey. Again, SDSS or Subaru Hyperspring-Cam, other important telescope surveys, and we got a nice constraint here. But those observations just focus on the bright sides. But James Webb is very sensitive to the faint object, and they put the many data points here. So surprisingly, so actually at the beginning of observations, we are very happy to observe many AGN. But as the time goes, it's kind of strange because the abundance of AGN is quite high. I mean, so compared to our expectation before James Webb, right, based on the ground-based survey, we had a kind of expectation following this green dashed line. But compared to that, actual abundance of the low luminosity AGN is 10 times or even 100 times higher, right? The number is so high compared to our previous expectation. So we are getting in trouble. So we don't really know, what physical processes, explain or populate such low luminosity AGN, abundant AGN in the faint and such high redshift universe. So this is very important recent hot topic. So keep in mind. Also, not only agent component. So James Webb also provides us a very important information about galaxy. I mean, host galaxy, hosting, host galaxy component and agent component. So based on the, variety of technique on the SED decomposition, so those kind of technique allows us to put the data point on this diagram. So here you see the diagram. The x-axis is a galaxy stellar mass, and the y-axis is a black hole mass. And the first, this is very complicated plot. But so if you look at the black hole and galaxy component at the nearby universe, okay, ratio 0, you see those gray dots. And I showed it at the introduction. So in the local universe, we have a nice tight correlation between black hole and galaxy mass, which is shown by this gray diagonal line. And compared to that, so all the James Webb data set unveil the overmassive population. Oh, sorry, overmassive population here. So most of the agent discovered agent system tend to be overmassive compared to the low redshift local tight correlation here. And this appear first, but two of them here, and this one, for this component, we also perform the better decomposition of quasar light from the underlying galaxy component. And we nicely perform this subtraction of quasar light and try to figure out the property of the host galaxy of this AGM. So based on that, we got the better estimation of the host galaxy, and we put the robust point on this diagram. I mean, galaxy versus black hole mass plane. But anyway, so comparing all the results, so right now, people got very excited because the kind of overmassive trend of the black holes relative to the local universe tight correlation. Yeah, so the natural question is, because many theoretical people, including myself, are very interested in what's the origin of supermassive black holes, and those new observation result by James Webb also give us a very important hint, because James Webb already unveiled the presence of overmassive black holes, right? So we should also explain the overmassive trend and the physical processes making, bringing black hole to overmassive region on this diagram. Okay, so then let me move on to the somehow theory part. So where I discuss the rapid growth process of the seed black holes. Right. So the situation is very complicated, but let me just summarize our theoretical understanding. So the seed formation can be done by several processes. So here I just summarize all the complicated physical processes into one cartoon picture. So depending on the property of the host galaxies, I mean super high redshift protogalaxies, and depending on the star formation environment, so the remnant mass of the seed black hole can be divergent. So if you think about normal situation, like a small galaxy, so we might have small stellar remnant black holes. This is so-called the population 3 black holes. But if you think about something special, like a peculiar environment, so host galaxies are irradiated by nearby star-forming galaxies. So this radiation change the chemical property of the primordial gas cloud of interest. So the kind of interaction with the galaxy environment, so bring the mass of remnant stars and the remnant black hole up to 10⁵ to 10⁶ solar masses. So far we have a bunch of theoretical explanations and the expected mass of the seed black hole. In the theoretical work, we got somehow, maybe not much, but somehow consensus, which is like, more massive seed black hole can be formed in the overdense region of the universe. So for example, so this is the dark matter distribution of the universe. So here you see the dense region. This is very crowded, and you see pink or red color, so which indicate a high density of dark matter component. And if you go to the outer skirt here, more like blue, so this is more like typical protogalaxy population. So as I say, if you go to the center of big city, like Madrid, in the dense region, we have a bunch of star-forming galaxies nearby. Those populations produce intense UV radiation, or your galaxy might experience very violent galaxy mergers. Okay, those kind of irradiation and the merger effect actually increase the mass of stellar remnant. So that's why we believe, in theory, that in the overdense region, we kind of believe, so it is kind of relatively easier to initiate massive seed black holes. But on the other hand, if you go to the low density region, it's like a countryside, so where we have a typical galaxy. In a normal environment, it is very difficult to increase the mass of the stellar remnant, and we basically have low mass or intermediate mass seed black holes. Then if I compile the recent radiation hydro simulation result into one plot, so here you see sort of stellar mass function or black hole initial mass function. The x-axis is the stellar mass or black hole mass, and y-axis is the number of those elements, those components. So as you can see here, if you think about the normal environment, you see normal black hole, right, ranging from 10 to 100 or maybe a few hundred solar masses. But if you focus on the overdense region, in a very dense region, in a big city in the universe, so the mass function shape is extended to 10 to the 4 or even 10 to the 5 solar masses. So taking into account this kind of process, so we got some sense about black hole seed formation. And the next step, so I try to put the black hole here, right, either countryside and the big city. Then I'm going to discuss the gas accretion process onto the black holes in each environment. But before that, let me just say one important thing. As you know, the black hole so black hole is quite small object, right? If you think about like a 10 to the 6 or 10 to the 7 solar mass black hole, so even though the mass is big, the size of the black hole is quite small, say microparsec. Then the black hole is hosted at the center of a galaxy, which has kiloparsec scale. So actually, so this problem can be solved or can be understood only when we cover such a wide range of physical systems, right? Starting from microparsec, like a black hole event horizon scale, up to galaxy scale, kiloparsec. So this is quite complicated and very difficult in theory, especially simulations. But so I'm going to talk about this like a multi-scale physics, but the key question is, okay, so forget about galaxy, but what about the black hole accretion in a near the black hole event horizon? So we have a nice result from the 2D, 3D radiation magnetohydro simulations. So as long as, so we get some kind of sense. So as long as the gas accretion, right, the supply from larger radii. So what I mean larger is like a galaxy scale. So as long as the gas, sufficient of gas is a supply from larger radii down to galactic nuclei, so basically black hole accept significant fraction of accreting matter. So when you study black hole feedback, you might have heard Eddington luminosity or Eddington limit accretion. But this is the case when the system is isotropic, okay, spherical symmetric system. But in reality, gas has an angular momentum and forming the disk component surrounding the black hole. So if you think about such kind of realistic situation, so the energy output by accreting flow and accreting black hole, so those radiation can escape, actually escape preferentially to the polar region. Then along the equator region, so radiation is actually trapped in the dense accreting matter. So the key point here is accretion rate is so high and the gas density in the system is also very high. So thanks to the such a high density environment, so radiation is easily trapped within the flow and everything just goes to the black hole. Then once the photon and the gas cross event horizon, so nothing happened, okay? This is a very useful garbage box. So by that process, radiation trapping is very useful and helpful to activate and encourage the rapid accretion onto the black hole itself. But key question is, so this is a very important assumption I made. So the question is, how can we supply such huge amount of gas from galactic scale? So this is a very important key assumption. So if the assumption is broken down, all the story is dead. Then, so let me go back to this diagram again. So if you want to discuss the gas supply from a galaxy scale, so we have a very important intermediate physical scale. So this is so-called the circumnuclear scale. So they're ranging from 1 parsec to 100 parsec. So this is exactly in between black hole event horizon scale and the galaxy scale. So here, I think you know this word, black hole gravitational influence radius, or in other words, black hole Bondi radius. So this radius is quite important because only within this radius, so black hole gravity dominates sound wave, gas pressure component. In other words, gas accretion actually starts after crossing this physical scale. Okay, so if you want to understand actual gas dynamics, like gas supply from galaxy down to black hole event horizon, we have to capture this intermediate important physical scale. So in my study, also many other people try to understand the global gas dynamics and try to make a bridge between the two different physical scales. So this is the point in the recent numerical studies in this context. Then, so as I say, so the black hole initial mass function really depends on the galaxy environment. Again, if you think about the very overdense region, the center of big city, so you have a more easy way to initiate massive black holes. But if you go to the countryside, so black hole seeding is more or less difficult. Okay, so the question is, okay, we know the initiation of seed black holes. Then what about the subsequent black hole growth? That might depend on the galaxy environment. So let me show you some example of the black hole growth and accretion processes. Okay, the first, let me focus on the typical protogalaxy. I mean, this is a galaxy in the countryside, the blue region, the outskirts of the big city. So in that situation, the gas, so the dark matter halo and the galaxy is less massive. So that's why the binding energy of the gas in the galactic nuclear is shallower. The energy is lower. As a result, the gas density is slightly lower compared to the cloudy region, well, as you can imagine. So in this situation, I put the black hole at the center and turning on radiation feedback. Then what's going to happen here? So here you see the 4 panels based on the radiation hydro simulation, including all the kind of complicated physics, especially ionization, reaction things. So here you see the right half right density and the left half temperature. Initially, gas component try to accrete to the central black hole, and the black hole start to shine, right? Produce radiation. Then this radiation make a bubble. Okay, here you see the low density bubble, and the gas is hot. And as the time goes, this ionization region start to expand and expand. Then eventually, this expanding H2 region cross Bondi radius. Okay, cross Bondi radius. Then afterwards, the gas supply from Bondi radius is strongly suppressed because the gas pressure around the Bondi radius is getting stronger due to heating. Okay, if you remember the equation, the Bondi radius, I don't know how to go back, but Bondi radius is a mass divided by sound speed square, which means mass divided by temperature. Okay, so gas heating is quite bad, right? The gas heating by radiation preferentially suppress gas accretion from larger radii. So as a result of this process, so gas accretion rate, the behavior become very much exotic, as you can see here. So the accretion rates try to be higher, but heating, right, the expanding, hot gas actually suppress accretion because Bondi radius gets smaller. Then they're repeating similar thing over the time. Then as a result, on average, so gas accretion onto the central region is pretty much smaller than critical Eddington accretion rate. So this is not great, right, in terms of the black hole growth. If you want to accelerate black hole growth, so this is a pretty bad situation. So this actually happened in a typical protogalaxy in high redshift. Then, but on the other hand, so what happened if you put the black hole at the center of the big city? So very overdense region where you have, relatively easily form massive super black hole. So we have a nice motivation to put the massive black hole at the center of the overdense region and start simulation. And here you see density, 2D density contour. So 1, 2, 3, 4, the time series. Initially, again, gas try to accrete and the black hole is shining. Then black hole produces radiation and H2 region, ionized bubble try to expand, right, as much as possible. But in the system, because the galaxy is massive and the binding energy of dark matter on the stellar population is really high, deeper potential, and the gas density is high enough. So that's why such a high density environment make the expansion of H2 region suppressed. Then eventually the H2 region start to collapse and encourage formation of the dense accretion disk surrounding the central black holes. So within the dense disk, so gas start to lose or start to transport angular momentum and activate very intense accretion onto the black hole. So this is the onset of super Eddington. Then afterwards, because of the huge accretion rate on the black hole, so the black hole is shining, producing outflows, all the feedback kicks in the simulation. So the accretion history is shown in the right-hand side. So here you see the time versus accretion rate. Initially, so this is pretty much similar to the previous case. The accretion rate is very episodic, right? Episodic, because radiation heating is quite essential and suppress gas supply from larger radii. But eventually, all the things just collapse to the galactic nuclei. At the same time, you see the big jump in the accretion rate, and the peak value reaches like over 100 Eddington. So this sounds crazy, but don't worry, this is only short time, very transient phenomena. And after the peak, accretion rate start to decrease with time because the feedback start to operate. They eventually come down to the normal Eddington accretion things. But anyway, in this situation, so unlike the previous case, so the average accretion rate is quite high, but at least in the short time scale, the million years or a few million years time scale, the accretion rate can be, substantially higher than Eddington accretion rate, which is quite important when you talk about black hole growth in the high Z universe. Then taking those kind of results, especially black hole growth in the overdense region. So I showed you this diagram before. galaxy mass and the black hole mass, the coevolution diagram. Then as I explained, so James Webb detected AGN tend to be overmassive compared to the local relation. And the overplot, okay, let me overplot the black hole growth and the galaxy growth based on the radiation hydro simulation, which I showed one slide back. So the evolution looks like that. So this simulation, I would say, nicely or consistently explain the presence of the overmassive population on this diagram here. So this transient super-Eddington accretion episode bring the black hole to overmassive region at the beginning. Afterwards, okay, feedback operate, but galaxy grow, all the things happen, but eventually follow the high mass ratio on this diagram. They eventually approaches kind of a normal region where we observe redshift 6 or 5 AGN quasar population. So this is a good thing, but also not only this calculation or this simulation can explain the presence of an overmassive black hole, but also this rapid growth process is quite important if you want to observe those populations, because in such an active young phase, so black hole, the AGN population can be bright enough to be detected or selected with the James Webb observations. So in the last 10 minutes, so let me briefly talk about the recent, I already gave you the overview of James Webb, but next section, I'm gonna discuss the kind of future prospect, okay? So how to improve our James Webb and AGN science in combination of observation and the theoretical calculation, also simulations. Okay, so this is the last section in my talk. So as I show you, the James Webb is a quite powerful and sensitive telescope, especially for hunting high Z objects. So in this talk, I focus on the high redshift supermassive black holes. And of course, James Webb is very powerful for hunting massive black hole population, as I show you in this talk, especially in the introduction. And in principle, so having the James Webb sensitivity, and if you put the AGN, accreting supermassive black holes up to, say, redshift 15, okay, redshift 15. So if you put the black hole redshift 15, the Lyman alpha, which is the brightest emission from the galaxy or quasar population, so this wavelength is redshifted to 2 micron in our observed frame. And looking at the sensitivity curve of the James Webb NIRCam, the imaging observations, so 2 micron is the best frequency for James Webb, best frequency, best wavelength. So which indicate, if we know the exact property of accreting supermassive black holes at the high redshift, so we can reach, such high redshift. Okay, we can, in principle, we can reach redshift 15 active galactic nuclei, and we might discover those kind of things. Then, the question is following. This is a very famous, nice, beautiful image taken by James Webb early data release. You see here, so many objects, right? So many objects. And if you're interested in high redshift objects, galaxies, AGN quasars, you need to find, or you need to look at the something red, because redshifted. But unfortunately, so this is our aim, right? We try to find quasars or massive black holes accreting, but unfortunately, it's quite difficult. Okay, as you know. So most likely, your red dots are just nearby galaxy, or maybe Balmer Break galaxies, or maybe very nearby our galactic brown dwarfs. So all the color looks pretty same, right? If you have only limited number of NIRCam filters, it's quite difficult to distinguish black holes and galaxies, and also galactic brown dwarf population. So to increase the efficiency of identification of the high Z supermassive black hole quasar population, we have to understand, okay, the nature of the radiation spectrum of the accreting black holes from high redshift environment. So here we try to figure out and try to make a prediction for this purpose. So I show you the simulation result, radiation hydro simulations in the few slides back. So using those data, and we apply the post-process radiative transfer calculation using cloudy code. And this is a very complicated technique, but combining cloudy calculation into the 2D density, temperature, chemical composition distribution, so we are able to reconstruct should be dense enough, okay? So using the high density environment, so this accreting flow produce very intense radiation into Balmer lines. So especially H alpha, also H beta, H gamma. But of course, as you know, H alpha is the brightest Balmer lines in normal situation. So then our prediction was, so especially H alpha is so bright, the equivalent widths for H alpha line exceed 1000 angstrom. The H beta is also quite high. So if we see kind of anomalous H alpha emitter from the James Webb data, so that might be the one important key signature to identify rapidly growing seed black hole population at high redshift. And also this is kind of minor thing, but if you think about dense region, so Lyman beta or high energy photon, Lyman beta can be trapped in the dense medium, and the Lyman beta should be reprocessed into the neutral oxygen line. So this is very, technical thing. But if the prediction is correct, we have to see like a 3 O1 line. It's this one O1 recombination line here. So using those kind of prediction based on simulation, so we try to propose what's the criterion, what's the kind of easier way to identify interesting object. I guess that this is my last slide. So taking those results, so as I say, super Eddington accreting seed black hole can be bright enough in Balmer frequency, so especially H alpha. So thanks to the brightness of the H alpha, so we discuss somehow useful plot for observers. This is so-called the color diagram. So here, as I say, for this system, H alpha is bright. So this H alpha is so bright, so bright that the so filter convo observed flux is also boost up due to the presence of a strong line. So using that, so like when the H alpha enter, in this filter, so this filter become brighter. So using this like zigzag pattern, so we propose the useful technique to identify seed black holes, especially here. And so let's see the right hand side. So the x-axis is the redshift, and the y-axis is the color between 4 micron and a 7.7 micron filter. So this color become red. I mean, red means positive big number. So when the H alpha enter this filter, okay, especially H alpha enter 7.7 micron filter, so we see some bump, okay? So the combining all kinds of things, and we construct the color diagram here. So this is quite complicated, but the message here is, so if you want to search accreting seed black holes, so you can use this combination of color diagram using near-cam filter, also MIDI, which is a mid-infrared camera installed in James Webb. And you search some object in the right top corner on this diagram. So there must be, or we believe that must be interesting. There might be very interesting sources. So I can also show the color condition. So if you're interested in, or you already touch public data from James Webb, you could also try hunting for seed black hole populations. But also beyond that, other papers, other researchers also propose the different technique or different criterion for hunting seed black hole population at a high-res universe. Okay. Then, so this is my final slide. So I talk about the many things, but still we have a big problem about the abundance of the low luminosity, also faint agent population. So hopefully, so by the technique, so using the technique I propose in the one slide back, we are able to observe and hunting those faint and low mass black hole. So this is quite important to differentiate, right, the model of seed black hole formation and the subsequent growth of those populations down to the reasonable redshift. So in the next few years, we hopefully we're gonna fill the gap. Okay, put more point here, also put more point here. So we are able to make sure our theory, calculation, or prediction is correct, wrong, or something in between. All right, so this is my summary, and I'm gonna stop here. And if you have a question, please just let me know.
Well, thank you very much, Kohei. Very nice and interesting talk. So we have time for a few questions. If you have questions, you can unmute your microphone and ask the question. YouTube. Well, I have a question, and I was wondering if in your simulation you include, for example, magnetic field, cosmic ray, and how they can affect the evolution of the black holes.
Yeah, so in those particular simulations, we didn't consider magnetic field. So this is pure radiation hydro simulation. But for radiation component, we consider the multi-frequency component ranging from infrared up to EUV, ionizing radiation. Also, we couple those radiation components with the chemical species in the simulation, like ionization, chemistry. So they are quite important to determine the gas cooling and heating. So baryon physics.
Yes, sure. And about the formation of the seed of black holes, do you consider also the merging between black holes? And if you have the we can say any instrument like to detect, for example, gravitational waves, which can form during the merging of black holes.
Yeah, in a seeding context, in a particular, our particular work, we didn't consider a thing, but so those intermediate massive black holes, high redshift, as a great candidate for the space-based GW detectors like LISA. It's a European and American programs. Also, the Chinese observation planning and Tianjin and Taiji. This is like a similar configuration. But using that, we are able to see, this is a signal to noise ratio contour. So if we have these detectors, we can see up to redshift, over 10 or even 20, those merging events. So we basically handle all the things, right, using GW detections. Also, the James Webb is a sensitive up to, say, redshift 10. So in a combination of the GW and the electromagnetic observations done by James Webb or maybe future Roman Space Telescope or Vera Rubin. So using that, so the multi-messenger astronomy in this context is quite rich and very promising.
Okay, thank you very much. Yes, could be very promising. And Are there any questions? Well, if not, I think we can thank the speaker again. Thank you very much for joining us, and see you next week with another IPARCOS seminar. So thank you very much to all, and thank you very much again, Kohei, for joining us.